Hello everyone. This video is about low frequency analysis of Cascode, and the low frequency response is normally contributed by the coupling capacitors. The coupling capacitor connected to the peripheral of the amplifier. Previously, I have introduced to you the basic structure of the so-called Cascode amplifier. So this is the basic schematic, but this one is not going to work on its own without any biasing. So to be able to make it work, we have to add the biasing network. So in this case, you may add the biasing network like in this manner. So we have R1 and R2 and R3. R1, R2, and R3. And the input is to be fed through a coupling capacitor, like this one here. So you also need to account for the wire resistance, RS here, and VS. So this is the view wave, and the base of Q2 is to be connected to ground, just like other common base amplifier. Then we have to add another coupling capacitor here. And obviously the output need to be filtered off all the DC component. So we have output, and maybe your output is connected to a low resistance. So let's say this one, this X, this is node X, and this is node Y. And this capacitor is called CY, and this capacitor is called CX. And this capacitor, this is node Z, yeah? So this capacitor is ZZ. And don't forget that we also need to have a capacitance here to adjust the tail resistance. So normally you can have a capacitor here, say C1. This is the C CG, yeah, CG. So we have to work out all the pole associated with each of these capacitance, the coupling capacitance. I think the easiest one that you can do is to start with the output one here. We know there is the output impedance here. We have already derived the output impedance. The output resistance here is RO, which is equal to the early effect, to RO2, and then RC. So we don't want to repeat all the analysis that you can see from other videos. The next thing that you need to look at is the equivalent circuit of the output. Now I'm going to draw the equivalent circuit of the output. We have RO here, and we have a capacitance here, C, Z, and this is not Z, yeah? And we have VR, RL, and the pole associated with this network, with this capacitor C2, uh, C of Z, is going to be P. I don't know what kind of name I should use. Normally, maybe I have just Z, yeah? Is equal to 1 divided by 2 pi. And then the R, what is the total value of R? RL plus RC, sorry, RL, and then the capacitance V. So this is the status means of derivation. 1 divided by 2 pi, and then L plus this amount of capacity resistance. If you have a low resistance, you need to add one more. Yeah. So I'm going to use uh, a red pen to highlight it. RL. Yeah. This is the newly added one. So this one is RL. And this one, I'm going to highlight this in this manner. Without the capacitance, without the RL way, there isn't any pole associated with this capacitance. So I hope you understand what I'm talking about. Again, I have to highlight this. So this is the pole frequency. This one is done, so I'm going to write down the intermediate bounding. So FPV is equal to 1 2 pi RL 2 R 2 in parallel with RC in parallel with RL. So I have to write the equivalent down. So this is done. Another easiest one that we can do, actually none of the one here is easy. No straightforward pole. What we can do now is to use Euler effects to resolve this law. We have a series, we have a capacitance R1, R2, R3 here. And R3 is connected to the ground. R1 is connected to the voltage supply, which is the AC ground. And the only one that is tricky is R2. R2 have no direct pathway connecting to the ground. So what we can do is to use Euler effect to resolve this R2 into a one resistance connect direct to the ground and another resistance connect direct to the ground. And this is the way how we found the parallel RC path combination. So the first thing that we need is to actual the independent voltage source here as ground, short circuit. So we do this first. Just make sure we don't have any contact. And here VCC is connected to ground, AC ground. Now, then everything becomes much easier now. We have RS, and then we have a bunch of resistance here. And we know the resistance input here is, we know that is R pi times 1 plus GM. 1, R pi 1, and then RE. We know this already. But the only thing that is tricky is R2. And how are we going to treat R2? We can use early effect. We can use mirror effects. Now we have this one, and we are going to resolve it into two resistance connected to the ground. So this one uh, is Rx, and this one is connected to the ground. And here we are going to do this the same. We are going to resolve it. This one is Ry, and we are going to use Euler theorem, and we are going to say now at node x we have a current going through this way, Ix, and we are going to end up with another current Ix, right? To make it exactly the same. So this is the network to be added, and this one is to be eliminated. So now, uh, according to here, Ix is equals to Vx minus Vy divided by the resistance here, R2. And we also, and this one is going to be replaced with this one, Ry. And this one is going to be Vx divided by Ry. Uh, so we have to find out what is, we have to simplify the circuit. Yeah, what we can do is to flip the top and bottom of this equation. So we end up with R2, Vx, Vy, and then Ryx. And Ry is going to be equal to R2, and then uh, uh, we have 1 minus uh, 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 Vy over Vx. So what is Vy? Vy according to here is R3 divided by R1 plus R2 plus R3, and then times VCC. And what is Vx? Vx is R1 plus, so R2 plus R3. And these two together can end up with a ratio of Vy divided by Vx being equal to R3 times divided by R2 plus R3. And now this is equation 1, and when substituting Vy divided by Vx into 1 and see what we can get. Ry is going to be R2 divided by 1 minus R3, R2 plus R3. And according to my calculation here, the value that we can get is here, R2 plus R3 at the end. So essentially, you will end up with, right, there are these two resistance, these two resistance, yeah, for node 1. So what we can do is we write down the important conclusion. Ry, this one is, We are dealing with Rx. We better write this down correctly. Rx, 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 and Rx. So Rx is the sum of these the two resistance. Okay. So we write down here the end result is R2 plus R3. And meanwhile, based on this assumption, uh, for the same analogies, we can write down this one is R1 plus R2. So we can do it briefly. So this one is going to be R1 plus R2. Yeah, the reason is if you use if you apply mirror effect again for this node, you will end up with the same result. So now this network is gone. We don't need this now. So I think this is the safest means of finding the low frequency nodes. And now here I think it is good enough. And then I can just move on. So uh, we have this node here, and we are going to find the pole associated with CX. So pole associated with CX is FPX, and it will be equal to 1 divided by 2 pi, and then R1 in parallel with these two capacitors. And then the capacitance Cx. And now, how about this one here? Let me see. Yeah, this one here. So this one here is going to be Fpy. It is going to be 1 divided by 2 pi. And then the amount of resistance here, we have R1 plus R2 in parallel with this one. This one is R3. And in parallel with what we know that we have already get the we can use the formula R pi 1 plus GM 1, and then RE, and then this is 1, and then multiplied by the capacitance associated with here. This not here, CY. So we have found this node, the node associated with CX, and we have also found the pole associated with CY, and we have found the pole associated with PZ. And what is the reason is here, CG. And CG has one resistance, RE2 connected to the ground. And it has another resistance. It's quite a complicated one. This one, and we also need to add the network here. And fortunately, we have used Euler effect, and we can significantly simplify the circuit here. So what we are going to do is to find out the resistance associated with with this node. This node is G. So RG is RE2 in parallel with this one, RE1. And do not forget that we have this resistance here. So 1 over GM1. And this one, and we also need to, because they are not in the same current, not in the same environment, you have to scale it up and move it into here. So we have this one, RB in parallel with R1 plus R2. This is the one. So now this is not enough because the resistance here is in another environment under IB. You have to move to the environment where the current is IC. So what we can do is divide it by beta. So GM1 plus this one, right, which is this resistance here. So this one plus this one, okay? Plus this one. So this is easier. Plus this one. And then you can do this now. So this is the resistance connected to RG. And to find the pole associated with node G, we need to find the capacitance. Yeah, so what we can do is V times CCG and then 2 pi and then 1. And this is FPG. So this is the, so altogether, we have found out all the poles here. And all these poles are associated with, all these poles are the low frequency poles. So at the end, you need to draw a ball part. The body part is you have the voltage gain V out over V in. We are going to get the magnitude and in dB. And we are going to have this is the rebound, and the low frequency pulse refers to here FP X FPY, right? We don't know which one comes first, and we don't know which one form the quantum frequency. It depends on the value. So if you have any questions, please leave your questions to the comments box, and we will try to answer your question. And thank you very much.